So yeah, I'm going to talk about little comparisons between the UTXO model and the account-based model, and I'm going to show you the technical reasonings behind why I think the UTXO based model scales even more, and then I'll talk briefly about why the project that I'm working on, Utreexo, helps scale the UTXO model even more. Okay, it's just a bit slow. So yeah, account-based models versus the UTXO-based model. Point there, okay. Yeah, scalability. UTXO model scales way better. And this is mainly because transactions, okay, so I want to talk about why the UTXO model scales better. And when we talk about scaling, how I view scaling is transactions per compute resource. This means that if you have some sort of compute resource, then you can do some amounts of transactions with that. And good systems will be able to do more on the same computer. So say, for example, if you have a computer like this, it'll do very slow. But if you have a computer like this, even if the model is very, very bad, even if the software is bad, the bad software running on good hardware will run faster than the good software running on bad hardware. So what I want to do is we have like the same amount of compute resources, but how are we able to squeeze more out of that? So yeah, software runs on hardware, and so we must write software optimized for that hardware. Right. So yeah, why does the UTXO model scale better than the account-based model? And that's really just because it has better concurrency. That's the only reason why the UTXO model scales better, because it has better concurrency. And this better concurrency allows us to have faster block validation. It allows for more transaction throughput for compute resource. So the same amount of computer, if we have the same good computer, the UTXO-based model will be able to do more transactions. So yeah, I want to talk about a little bit about concurrency. So this is not concurrent at all. This is very sequential. This is 4 people lined up to buy sodas in a vending machine. But if we have concurrency, what we have is we'll have 4 extra people, and we'll have 2 lines. So this is still bottlenecked by 1 vending machine. So if the vending machine is really, really slow, then the sodas, it takes a while. But if we have 2 vending machines, because we're able to have concurrency, we're able to split up the work. So now we're able to double the speed that people are able to get their sodas. But what bad software will do, what not concurrent software will do, is even if there's 2 vending machines, they'll only go to 1 vending machine. And even worse software, even if there's 3 vending machines, they'll all queue up into 1 vending machine. And I'll show you the differences between how the UTXO model does this and the account-based model does this. And so why the UTXO model scales better? The UTXO model, the UTXO state changes are per block. So it only changes after a block has been confirmed. It does not change in between. And so what this allows us to do, it allows us to validate transactions out of order. So it doesn't matter if we validate transaction number 10 before we validate transaction number 1. We could all be validating them at the same time. And this is concurrency. The account-based model is sequential. What this means is, and why it's sequential is because the account state changes per transaction. So we can't verify transaction 10 before we verify transaction 1. And so it's not safe to validate transactions out of order. So everything is sequential. So if we have a UTXO model, we just replace the vending machine with the CPU core and 10 transactions. So right now, because the UTXO model is concurrent, when we have one CPU core, it's not any faster. But if we have 2 CPU cores, then we're able to split up the work. And if we have 4 CPU cores, we're able to split up the work even more. But this, how the account-based model has to do, what they have to do is they have to do it sequentially. So the same 10 transactions in the UTXO model, we're able to split that up, but in the account-based model, you can't. You cannot split up the work because the account state will be changed after one transaction. So transaction 4 can become valid after the process of transaction 1, 2, and 3. Vice versa, if transaction 1, 2, and 3 can make transaction 4 invalid, and so we cannot do this out of order, and so we have to line them all up at one CPU core. So yeah, 20 years ago, I think a lot of people remember this. This is when Intel started putting 2 cores in computers, but nowadays we have so much more cores. And recently, AMD released their latest models of CPUs, and the base model, the crappiest CPU you can get, has 6 cores. So we're increasing the number of cores that a computer has. And in a sequential model, the speed of a single core matters much more than how many cores that we have. So this is a chart from CPU Benchmark, and what it shows is it shows 2 things. So this is performance benchmarks of a desktop CPU, and if you look over here, this is this verification speed of a UTXO based model. Why is this so? Because this line that you see is just the desktop, and the line that you see on the bottom in light blue is per core, like per thread. So because a lot of these computers have multiple cores, all these cores work together to process more things. And because with the UTXO model, we're able to split up the work in between cores, we're able to take advantage of all this speed improvements in CPU design. But the account-based model can't. They have to rely on single core performance. And single core, like single thread performance has not been increasing that much compared to, it has been increasing, but it's not increasing as much. So, like based on the hardware, we're able to squeeze more transactions. We're able to validate more transactions with the UTXO based model. And even further, so what I did was I went even further and was benchmarking both the Bitcoin and Ethereum Classic. And so I'll show you some visualizations on what each node is doing, like what each node is spending time on. And yeah, so as I mentioned, I'll be using CoreGet. I was using Ethereum Classic, and BTCD, which is a Bitcoin implementation in Go. So this is for Ethereum Classic, and this is just all the processes. This is a visualization of all the processes that the node is doing. And it's kind of hard to read, the texts are small, but I will point out these things. So you'll see these red boxes. Each of these red boxes highlights the operations that the Ethereum Classic node is doing. And all 4 of these boxes are database operations. So I made a pie graph of what the Ethereum Classic node does. And 53% of the time, it's doing database operations. 20% of the time, it's doing headers verification. So half of the time, what an Ethereum Classic node is doing, it's fetching from the disk. So it's bottlenecked by the disk. Yeah, 53% of the time on disk operations. So if I were to visualize this even further, so this is the transaction verification for like account-based model using Ethereum Classic. So we take a transaction. We have to first, and this is like a simple, just not a smart contract, but this is just a transaction. So what we do is we fetch the account state. For this transaction, fetch the account states. And then the CPU core gets it back, and then we're able to do some verification on it. And if the verification passes, then we write that to the disk. And that's transaction number 1 done. And then transaction number 2, do the same thing, you get it. You read from the disk, you get it back from the disk, do some additional verification, and then you write to the disk. So this is a very slow process. And Yeah. So so I want to show you what BTC does, which is Bitcoin written in Go, and the graph looks very different. And the red circle is the CPU operations, or it's the transaction verification operations, and the yellow circle or yellow box is the Go runtime. So this is what Bitcoin mostly spends time on, and this is particular to BTCD. So 48% of the time is signature verification, and 44% of the time is the Go runtime, which is also CPU based. So those two added together, 92% of the time, what Bitcoin is doing, it's doing CPU operations. This is versus what Ethereum does is it's all disk operations. And what this means is that we're able to just utilize the CPU more. And so if we were to visualize what Bitcoin does, is we take one CPU, and one CPU will will operate, and so we'll read all the inputs of the transaction. So we'll read all the inputs, and then we have all the inputs cached in memory. Now we're able to take each transaction, verify it, write it to disk. Take each transaction, verify it, write it to disk. And so we're able to process much, much faster than what the account-based model is doing. And so this is a graph that I made of the Samsung SSD performance since 2013. So this is about 10 years worth of performance improvements in SSDs. And the important part is if you see the blue and the green lines, that's just random reads and writes. And so this is this is multiple things being read at the same time. If you see the random read and random writes with a QD1, that means a Q depth of 1. So it means how fast does it take to get one single thing off of disk. So if the line that's increasing a lot, that's reading multiple things from the disk. Like the UTXO state model, we're able to read all the UTXOs at the same time from the disk. So what we're actually doing is we're doing these random reads that we queue up a lot. And so the Samsung SSDs have been improving in the random reads and writes, while they have not been improving in single operation read and writes. So this is what we get with the verification of a UTXO based model. However, because we have to read one thing at a time in an account-based model, the speed is limited to here, which is the reads and writes of Q depth of 1. So now you can sort of see how the account-based model is just not able to take advantage of all these improvements in hardware technologies. And I want to talk briefly about how Utreexo makes the UTXO based model even better. So with how Utreexo works, I won't go into detail, but we can now verify blocks in parallel. So not just transactions, but blocks in parallel as well as the ability to verify transactions in parallel. And so this is the same exact thing, except before it was 10 transactions, but now it's 10 blocks. And within each block, we're able to validate all the transactions in parallel as well. So back in 2021, I did a comparison. I did a test of, hey, like if we have this Utreexo based model versus how Bitcoin works today, how much faster would it be? This was how much it was faster. This was about 63% faster. And you'll see that Bitcoin Core did about 174 till block height of around 650,000, while the node that had Utreexo applied was able to do it in 107 minutes. So way, way faster. And because of all the algorithm improvements that we had since then, we're able to, if we did the benchmark now, it would be even faster. And so this is just, so Amdahl's law talks about how parallelization only helps if there's a lot of things that you could parallelize. And this graph is just, it's a straight line, and what it shows is that if we're able to throw more computers in there, we're able to have the speed up of, we're able to have this very linear speed up. So it's only matter of compute resources that you throw at it in the Utreexo model of like all these all the speed improvements and the parallelization that we can have. So yeah, in conclusion, yeah, this was back in 2005. We talked about how the free lunch is over. And back in 2005, because single-core Intel CPUs were still able to give more performance, we didn't have to write software optimized for the hardware. But now it's not. We have to write, each single CPU core is not getting any faster, so we have to write software for the hardware. We have to be concurrent. And so, yeah, the UTXO model scales better because we have parallelism, we have concurrency during transaction validation in a single block, and we're not bottlenecked by disk I/O. And with Utreexo, it becomes even better because we have parallelism with validating blocks, and we eliminate disk reads and writes. Yeah, thank you. These are the slides again, in case you liked my presentation.